Computer vision is one of the hottest topics in computer science research today, with tons of exciting opportunities such as tumor identification in healthcare, automatic inventory taking in supermarkets, Face ID in your cell phone, and even in self-driving cars, as we see at Tesla and Google. It's understandable why computer vision has become one of the most exciting fields of artificial intelligence. Underlying the machine's growing ability to understand images are constantly evolving algorithms and architectures. The development of MaskRCNN algorithm, standing for Regional Convolutional Neural Network, has allowed computers to process and understand images in a way they have not before. In this video, we will first talk about the image segmentation task, which is a problem that MaskRCNN addresses. Then we will talk about what a convolutional neural network is and how it operates. From there, we will talk about the building blocks of MaskRCNN, how they work and how they've evolved from the original RCNN to FastRCNN to FasterRCNN, and finally to MaskRCNN. Lastly, we will show a quick demonstration of our own implementation of MaskRCNN and discuss the different applications and impacts that this research could have in all of our lives. So what is instance segmentation? Instance segmentation is the task of identifying object outlines at a pixel level. To better understand what this entails, let's look at the main four classes of problems in detection and segmentation. Semantic segmentation divides the image into regions of pixels that are related to one another. There are no objects, only pixel groups. In classification, we determine the main focus of a picture. Localization further tells us where the object of focus is located. Object detection is a form of repeated classification and localization on a single image where we find multiple objects of interest, classify them, and box them. Lastly, instance segmentation is an extension of object detection in that not only do we need to find the relevant object and their locations, but we also need to find pixel by pixel where they are located. Having an understanding of convolutional neural networks, or CNNs, is critical for understanding MaskRCNN. Convolutional neural networks are a type of deep learning algorithm used to classify images. They have an advantage over the feed-forward neural networks discussed in class, since CNNs are able to capture the spatial dependencies through the application of image filters, rather than flattening out the image into a column vector at the very first step. The CNN algorithm works as follows. First, the image is convolved with a filter. This process multiplies different segments of the user input with a smaller weighted matrix, the filter, to generate a new matrix. This process allows us to extract different features, such as edges, from the input image. There can be multiple filters at each convolutional layer devoted to capturing different features, such as edges, colors, and gradient orientation. After every convolutional layer, we have a pooling layer that is responsible for reducing the spatial size of the convolved features. Pooling is used to reduce noise, to better extract dominant features, and is also useful for reducing the computational complexity of the image matrix. Pooling is usually done by either calculating the maximum or the average of the elements of a region in an image. The convolving and pooling steps are repeated multiple times, with each iteration reducing the dimensions of the image matrix. Finally, we arrive at a feature vector, which we feed into a regular feed-forward neural network we call a fully connected layer. The model classifies the images using softmax or SVM or some other loss function. There are a wide variety of convolutional neural networks available. However, what's important is just to know that CNNs consist of convolutional layers, pooling layers, and a fully connected layer. To understand MaskRCNN, it helps to look at its predecessors, namely the original RCNN in 2013, FastRCNN in 2015, and FasterRCNN published later that same year. These papers are the foundation for MaskRCNN. Let's start with the original RCNN, which was used for solving the object recognition problem. In RCNN, after we input our image, it first goes through a step called region proposals, during which around 2,000 regions of different aspect ratios are extracted from various locations in the image. RCNN is agnostic to the region proposal method, and we can use different methods such as selective search, objectness, multi-scale combinatorial grouping, or any other algorithm. These region proposals then get warped into a fixed size in order to have a fixed input dimension for the CNN, which in turn produces a feature vector as an output. Rather than using a softmax loss function at the last step, the original RCNN researchers opted to use SVM for object classification. After all these steps, RCNN refines the bounding boxes of the regions of interest and outputs the object labels with the corresponding boxes. However, RCNN has a few flaws. First, training is a multi-stage pipeline with RCNN first fine-tuning a CNN on top of object proposals, then fitting SVMs onto the CNN features, and finally learning the bounding box regressors. With a 5,000 image dataset taking 2.5 GPU days to train, creating a model is a computationally expensive process. Furthermore, real-time usage of object detection is very slow because the CNN forward pass is made for each object proposal region without sharing computation. One image would normally take about 47 seconds to fully process and identify. Needless to say, we can do better. FastRCNN, like its predecessor, is oblivious to the region proposal method. One major difference, however, is that the CNN forward pass is only made once on the entire image, rather than on each region of interest. For each region of interest, we extract its corresponding features from the CNN feature map that was created over the entire picture. From here, each region of interest undergoes the pooling process in a single layer to map the ROI into a small feature map. The size of this feature map is a tunable hyperparameter. This information is then passed onto a fully connected layer and uses a mixture of softmax classification and linear regression to find the object class and bounding box. Furthermore, in FastRCNN, we're able to train all the parameters, including the CNN, together using a log loss function from the object classification and an L1 loss function from the boundary box prediction. FastRCNN trains 9 times faster than RCNN and is an entire 213 times faster at test time. To top it off, FastRCNN also improves detection accuracy. However, region proposal times are still slow and can take up to 2 seconds on a typical CPU. FastRCNN solves this by replacing the region proposal method with an internal deep network named the region proposal network. This network takes the feature map as input and outputs the region proposals. These proposals are then fed into the same ROI pooling layer from FastRCNN. The region proposal network is trained to predict the probability of a particular region being an object or background, and also a corresponding boundary box. The network is created by moving a sliding window over the feature map and determining whether the corresponding anchored boxes intersect significantly with a ground truth object. With the region proposal network, image testing is 10 times faster than its predecessor, with similar performance and accuracy. Until now, the algorithms we've covered dealt with object detection and recognition. To make the leap into instance segmentation, an additional neural network is used to generate a binary mask that outputs ones where the pixel belongs to an object and zeros everywhere else. The creation and formation of this neural network has been researched heavily for the semantic segmentation problem outside of this paper. Note that MaskRCNN applies a binary mask onto each region of interest in parallel to predicting the class and box offset, which is different from its sister algorithms where classification depends directly on the mask predictions. In addition to adding a binary mask, one more clever change had to be made for MaskRCNN, which is to replace the ROI pool step with a more precise process called ROI align. In ROI pool, we quantize and round down pixel values to integers during calculations as we only need to draw bounding boxes. However, since instance segmentation requires pixel level specificity, ROI align uses bilinear interpolation and floating points to get sub-pixel accuracy during computations. MaskRCNN shows significant improvements compared to the previous winners of the COMP3314 and 2016 competitions, with relative increases in average precision ranging from 20% to 50% under some contexts. It was used by all 3 winning teams at the 2017 COCO Instance Segmentation Competition, which is the year it was published, and all had significantly outperformed the previous state of the art. In this clip, you see our own implementation of MaskRCNN on an iconic view of Pokeland Road. For this test, we split the incoming video into frames and repeatedly applied our model onto it. In the original paper, the testing was done only on still images. This demo reveals that image testing is fast enough to support a roughly 20 frames per second video. MaskRCNN has a huge potential for impact, as it is both a powerful and a flexible system, with obvious uses ranging from traffic monitoring in cities to collision avoidance in cars and robots, as well as more hidden uses such as human pose estimation and video editing without green screens. This paper opens the door for a virtually limitless number of applications. Visit our GitHub page to learn more, compare models trained on different datasets, and experiment with a variety of test data.